Hey, as I mentioned earlier, our exponential decay is modeled by the exact same equation where your A is still your initial value, but your B, instead of being a growth factor, it's the decay factor. And instead of taking 100% and adding the percent you're increasing by, you're going to subtract the percent it's decreasing by. All right, here we're going to actually do some individual calculations here, and then we'll create the model or the equation for this. So calculate the car's value at the end of each of its first 5 years by completing the table. So we start with $25,000 car and then have it depreciate in value by 15% per year. So at year 0, when you first initially purchase it, it's $25,000. So if you're decreasing by 15% each year, that means you would actually have 85% of the value remaining. And that's because 100% minus 15%, so 100% minus 15% is actually equal to 85%, or 0.085. Sorry, 0.85. I added a 0 in there when I said that the first time. So what I can do with this value is times by 0.85 to get what it's worth at the end of the first year. And I get $21,000, $21,250 there. Now, that value decreases by 15%, or we're going to take that amount, that new amount, and times it by 0.85. So we're not subtracting the same amount every time. That would make it linear. We're going to have $18,062.50 as the value at the end of the second year. And again, times by 0.85 to get 85% of that. We get $15,353. And I'm going to take money to 2 decimal places. That's going to round to 13 cents here. And then we're going to times by 0.85 again. So we're just finding 85% of the previous year's value and rounding that. I'm leaving all the decimals in my calculator, but what I'm writing down is rounded to 2 decimal places. And times that again, and I get $11,092.63. All right, so we're going to create a model here to calculate the value. So the value V, we initially start with $25,000 as its original value, and then our decay factor is this 0.85 here, 0.85, because it's the 100% minus the 15%, and then N would be the number of years. So if we wanted to check that, like if I wanted the 5th year's value, we could do 25,000. We could go directly to that without having to times each one by 0.85, and we could put a 5 here. And if you put that in your calculator, I'm just going to double check that, to the exponent 5 times by 25,000. Here we are. Yeah, I get the exact same value as what I have written in the chart. All right, so the value at the end of the 10th year, we're just going to sub a 10 in for that exponent. 25,000 times 0.85 to the exponent of 10 will get its value. And I get $4,921.86 would be its value at the end of the 10th year. All right, and then in what year, so we're solving for the exponent now, the N is the question mark, does the value reach 7,000? So it's definitely before 10 years, because at 10 years you're less than 7,000. So we would put in 7,000 for the value. 25,000 goes here, 0.85 to the N, and then we use divide both sides by 25,000, and then use guess and check to come up with the approximate year that will work. 7,000, that's not going to be a pretty number here. That gives, oh, it's not too bad, 0.28. 0.85 to the N, and then guess and check with that. So I've checked N being 7 and N being 8, and 0.28 is somewhere between those two things. So during the 8th year, by the end of the 8th year, it has fallen to less than 7,000. Sometime during the 8th year, it reaches the value of $7,000. And of course, I can finish up these word problems with some final statements at the end. All right, example number 4. A hospital uses cobalt-60 in its radiotherapy treatment for cancer patient. Cobalt-60 has a half-life of 5.2 years. So this is a special case where we're talking about half-life. What that means is the time it takes for the mass to cut itself in half. So 5.2 years for the mass to decay to half of its original amount. The hospital has 80 grams of this cobalt-60. It requires at least 25 grams for the therapy machine to provide an effective amount of radiation. So if it's starting with 80 grams, in 5.2 years, it will be down to 40 grams is what that means. And then in 10.4 years, so I'm just doubling this, it will now be cut in half a second time. So it will be down to 20 grams. So definitely before 10 years, it will have decayed to an amount where it needs to be replenished. So in terms of what we have here, I don't know why I have 64 here. This should be 80. We'll make this 80 here. So in 5.2 years, that mass is cut in half. It's now 40 grams. And then cut in half again another 5.2 years later. So now there's 20 grams. And then another 5.2 years later, it's cut in half again. It's now down to 10 grams of cobalt. So now I need to add another page here to finish up this example. So for this part, we want to actually write the equation to represent that mass. Now initially, our initial mass, our A value, was 80 grams to begin with. And we had a half-life. So remember when we had doubling, something was doubling, the base was 2. If you have a half-life, you've got 100% and you're reducing it by 50%, it leaves you with 50% or a half. So you can either use a half as your base or you can use 0.50, whichever one makes you happier. All right, so our mass will be given by the equation of 80, and then you can use either a half or 0.5 here. And then, now T is our time in years. Now remember with that doubling question, when we switched it to every 30 minutes, we had to take our time in minutes and then divide it by 30. Here, time is in years, but we want to see how many groups of 5.2 that we can make out of it. So we want to take our time and divide by 5.2 to see how many groups, how many times it actually cuts in half. So how much of the original amount will there be after 1 year? So it will definitely not have cut exactly in half because it needs 5.2 years to do that. So we're going to calculate the mass here by subbing in 1 for our T. Whoops, wrong number. So we're going to put a 1 over 5.2. Now, depending on how your calculator works, you might have to put this in the exponent in brackets. So I'm going to do 0.5 to the exponent, and I'm using my bracket button here. 1 divided by 5.2, close that bracket. So my exponent's actually 0.1923, yada yada. That gives me 0.8752, yada yada, and then I'm timesing that by 80, and my yada yadas are just a bunch of other decimal places after that. So that gives me about 70 grams. There are some other digits after that, but about 70 grams would be left after 1 year. All right, now how often must the staff replace the cobalt to the nearest month? So time is in years, so we're going to need to take that to a decimal place or 2 to be able to come up with the months amount. We want to know when is that mass going to equal 25. So 25 will be in for the mass, and that's equal to 80, 0.5, t to the exponent t over 5.2. Divide both sides by 80 to start getting our exponent by itself. Divide by 80, and then 25 divided by 80, that gives me 0.3125, and that's equal to 0.5 to this exponent. Now, what I'm going to do is just try different exponents on 0.5. 0.5. Now, if we go back to our chart, we know that it wasn't going to be 10 years. Let's try 8 and see what happens here. And I got a value of 0.344, which is a bit bigger than what I want. So let's try 8.5 and see what happens with that one. Now, I tried a bunch of different things here just to see what I got, and I found this one, when T was 8.73, I got pretty close, so let's go with that. Now, that's 8 years and a bit. It's almost 3/4 of a year. I'm just going to take that 0.73 and times by 12, since there are 12 months in a year, and 0.73 times 12 gives me almost 9 months. It's 8.76 months. Okay, so definitely you want to replace that by 8 years, 8 3/4 of a year roughly. We could have gone with this one. 8 years, 8 months, 8 years, 9 months, somewhere in there. So hopefully at this point you're able to read a word problem, develop an equation for that word problem, exponential equation, and solve that problem. When you're solving for the exponent, you just need to remember you're going to use guess and check for that for now, or you can sneak it into Desmos and solve it that way as well. All right, good luck.